All right, so let's introduce polynomials here, or at least applications of them, using a real-life situation. So the U.S. Postal Service, they have some requirements on the packages that they accept. So they will not accept rectangular packages if the perimeter of one end of the package plus the length of the package is greater than 130 inches. So let's consider a rectangular package shown here with square ends. That's going to be key, just so we can kind of make the math on this work out. The key is that we're going to make the height and the width of the package equal to each other to make the end a square. Otherwise, we would just have too many variables, as we'll see in a little bit what I'm talking about. But let's see if we can dig into this a little bit. So they're not going to accept a package if the perimeter of one end, right up here, plus the length is greater than 130. So basically, the perimeter plus the length, and let's just say that it equals the full 130. What we're going to try and do in a minute here is maximize the volume. So we want to use like the full 130. I know it says it should be less than that because they won't accept it if it's greater than 130. But let's just set it equal to 130. And then let's think about the actual perimeter, okay? The perimeter of the base. If we see the base is that yellow square though, so the perimeter of an object is the distance all the way around. Okay, so the perimeter of the base there is just going to actually be 4W, right? If we take a look at, again, here's the base, W, 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 and W. So the perimeter is 4W plus L, okay, needs to equal 130. And what I'm going to do, I'm just going to solve that for L so we can use that in a minute. If I subtract the 4W from both sides, this is telling me that the length, or L, must equal 130 minus 4 times W. Okay, so we're going to kind of use that equation to help us get things going in a minute here. But let's just jump in and see how things are looking. Okay, so if we think about, we're going to have different widths and different lengths, and we're going to see what the volume is going to be. I'm going to fill this table in down here. So with our group, okay, we're going to do this. I'll do it for you guys. They're not in a group setting. Let's assume that the perimeter of one end of the package plus the length equals the 130. Okay, so we already kind of set that up. Let's complete the table with some possible measurements for the length and width, and then we'll find the volume. Okay, so I'm just going to make up a width value. Let's say if the width were 10 inches. Okay, I'm just making that up. If the width were 10, the length then, remember we saw the length is always going to equal 130 minus 4W, okay, from the equation over here. So if we make up a width, let's say 10, we can find the length. If I do 130 minus 4 times 10, that would give me a length of 90. Okay, and again, what that's doing, that's making the perimeter. So the perimeter of the one end would be 10 plus 10 plus 10 plus 10, or 40. Then plus the 90 would get us to the full 130. Okay, and to get the actual volume of that, of those dimensions, volume, of course, equals length times width times height. Okay, now here's why in this situation we're making the height and the width both equal to W. So I could rewrite that as length times width, and the height is also W. Okay, and what I'm going to be able to do is write that as L times W squared. Okay, because it's width times width. So to get the volume, what I'm going to do for this first one, I'm going to do the length of 90 times 10 squared. So 90 times 10 times 10 is going to give me a volume with those dimensions would be 9,000. Okay, let's pick another one. Let's say, what if the width were the 15? Let's just make a nice 15 there. Okay, so if the width were 15, I can find the length of the package by doing 130 minus 4 times 15. Okay, again, just using this formula to find length. So 130 minus 4 times 15 is 70. Okay, and then the volume, I'm just going to use this formula, length times width squared. So 70 times 15 squared, which gets me 15,750. Okay, so what we're doing, we're just making up different values for the width. Okay, seeing what the length would be and then figuring out what the volume would be. What if we did, I don't know, let's say we went to 20. Okay, if the width were 20, the length would be 130 minus 4 times 20, okay, which is 50. Okay, and again, that would make us have the full 130 inches being used here. And then the volume is that length, okay, so 50 times 20 squared is 20,000. All right, and let's do one more. Let's say, what if we went up to, I don't know, 25, right? What if the width were 25? Okay, the length, again, would always be 130 minus 4 times 25. So in this case, that would end up being 30. Okay, and if we wanted to get the volume of that shape, so again, it's length times width, so 30 times 25 times 25, the volume there would end up being 18,750. Okay, and let's just do one more. What if, I'm going to skip 30. Let's say we go to 40. What if we wanted to have a width of 40, for example? Okay, if the width were 40, the length is 130 minus 4 times 40, and I'm getting a negative number in there. I'm getting negative 30. Okay, is that possible? Are you going to have a package with a negative length? Probably not. Okay, so something happened, and again, the idea is, or the reason that is, see if you can reason this out with me, is that if the width were 40, then that perimeter, 40, 40, 40, 40, that would be 160. Okay, now remember, the perimeter plus the length can only be 130. So that width of 40 is taking up more, more materials than we need. Okay, so there's not an unlimited amount of material we can use here. So can we, looking at this here, can we give an estimate? What's the largest possible volume? When you ship a package, a lot of times you want to fit as much in as possible. So what's the largest possible the volume could be? Looking at our numbers here, the biggest volume we saw was the 20,000 here. Okay, do we think that it's going to be possible to get more than that? I don't know. But maybe around 20,000 based on the numbers we used is kind of the estimate that I might give. Table here, we put some values in for the width, and when the width got too big, we ended up with a negative length. Okay, so like remember we tried to use 40 and it didn't work out. When we used 40 right here, we got the negative length. So 32 point, just to put this together, the first one we did, when I did a width of 10, the volume was 9,000. All right, so let's keep looking at this here. Let's jump up here. We're down to the bottom of the page. Use the package described in item 1. Let's write an expression for length. Okay. If we remember, we kind of already did that, but let's just put it back together. The condition was that 4 times W, right, the perimeter, so 4W plus L needed to equal 130. So the expression for L, when we solved that for L, right, we subtracted 4W from both sides. Okay, we ended up with L equaled, here's the expression, 130 minus 4W. Okay, so there's the expression for L, and we used that already. Okay, so now part B, let's write the volume. If you remember, volume is length times width times height. Okay, that's volume of a cube, when the base is a square like ours is, or any cube actually, a rectangular prism I should say. In our specific example, the height and the width were both the same. Okay, so they were both W, which allowed us to write it as L times W squared. Okay. Now what we want to do here though in part B is we want to write the volume as a function of W. Okay, so meaning I only want to have W's in our expression here. So here's what we're going to do. We're going to do a little substitution. Okay, volume is length times width, right? We know up here that this is equal to L. So where that L is, I'm going to replace it with 130 minus 4W times W squared. So what we did, we took this 130 minus 4w and I replaced L, or I substituted 130 minus 4w in for L. And the reason I did that was so that we would have a function in terms of a single variable. I know that the volume equals 130 minus 4w times w squared. I did that so that we can graph this thing, okay? The w is going to be like our x value, and I can't leave it like this because it has two variables. It has L's and W's in it, and we can't graph, yet until you get into like third year calculus or whatever, three variable systems, graphing in 3D. Okay, so what we're going to do is graph this thing in a minute here, and we're going to find the maximum of it, okay, and we're going to see what really is the maximum volume. Okay, so let's take a look. Let's keep digging in a little bit here. I'm going to skip part C. Part 4 there. Consider the smallest and largest possible values for W that make sense. Okay, if you remember when we did, so which values kind of make sense? So if you think about, first off, I'm not going to have a negative width, right? So I know that 0 must be less than W. Okay, or W must be greater than 0, right? We can't have negative. But also the other thing is there's a certain maximum, and the trick to finding that is this expression, the 130 minus 4w, that is the length, right? The length can't be negative either, right? So 130 minus 4w must be greater than 0. Okay, so if we solve that thing, okay, I'm going to add 4w to both sides. 130 is greater than 4w. And when I divide both sides by 4, I'm going to get 32.5. Okay, so we have that 32.5 must be greater than W. Okay, so we have two statements. W has to be bigger than 0, can't have a negative, but then also W has to be less than 32.5 as well. Okay, that's going to force the situation to work out. If the width were bigger than 32.5, we would run into that case where the length ends up being negative, like we saw in the previous example. I think we used 5 is really like the biggest that the width could be. Okay, so let's take a look. I'm going to graph this thing. I graphed what I graphed in Desmos right here. Here's the function. Okay, right here. This is basically the 130 minus 4w times w squared. I just use x, okay, instead of w. And you see it's this graph of a polynomial function. Okay, it has, as we talked about in the first section, it has so 0, 0 is a relative minimum. Up here, though, is our key. That's a relative maximum right there. And then we see down here, this is going to be the x-intercept. Okay, and let me just take a step back. What I've shown graphing here, the x values is the width. Okay, so different widths are going to provide different y values, which are volumes. Okay, and we can see, like for example, let me just go back to, okay, you'll see that point, the width of 10, the volume, the y value was 9,000. So that's what this graph is showing. Okay, it's showing width and volume. Okay, so you see the maximum there. When the width was 21.7, the x value is 21.7, okay, that gave us a volume, a maximum volume, and I got these coordinates from Desmos, from the graph, okay, I clicked on the graph. The maximum possible volume was 20,342, okay, that occurred, let me just write some of this down, the max possible volume is 20,342. That occurs when the width, okay, the x value is 21.7 inches. Okay, the volume is inches cubed. So the x and y coordinates can find you the maximum, but we need to know what they mean. Okay, the y value is the actual volume. The x is just the width that got you that volume. Okay, so if I ask you what is the maximum, you need to give me the y value. Okay, if I ask you where does that maximum occur, then you give me the x value. Okay, make sure you can interpret both the x and y coordinates. Okay, last thing on this, take a look at the x-intercept down here that we showed. A little bit past 30, we see this graph hit 0. Okay, that is the 32.5 value that we had right up here. Okay, if the width gets any larger than that, okay, if x gets past 32.5, okay, you can see that the volume down here is negative. Okay, so that's why this thing kind of really only makes sense for these x values between 0 and 32.5, because that's when you get a positive volume. Okay, and that would tie into what's known as the domain of the function, which x values kind of make sense. Okay. All right, so we got the coordinates of the max and min. Let me just let's set up a little bit of this, of the homework, okay? I want to look at number 17 real quick, the setup on it. So this will be the assignment. On number 17, it's asking you to find the maximum, eventually, of a cylindrical tube, okay? So let's just kind of make sure we're clear on that. So with 17, okay, cylindrical tube, so it's going to have like a circular base. Okay, the top and bottom, and it's going to have a radius. So radius of a circle, right, is half the diameter. So from there to there, and then the height, of course, would be the height. Okay, so let's set this up a little bit. They're telling us the condition, okay, that they give us is that the height of the tube plus twice the radius must be less than 60. Okay, so let's see what that means. The height, so h, plus twice the radius. Now, I know it needs to be less than 60, but let's assume it equals the full 60, okay? Because we're going to want to maximize volume, so let's use the whole allotment that we have. Let's say it equals 60. Okay, what part A is saying, write an expression for h in terms of r. Okay, so basically they just want us to solve this for h. Okay, so we'll do that together. If we solve this equation here for h, we would just subtract 2r from both sides. The height is going to equal 60 minus 2r. Okay, so that's the height. Now part B is going to ask, write an expression for the volume. So I want to make sure we know the formula for volume. So the volume of a shape like this, okay, in general, volume is basically like the area of the base times the height. Okay, so in this case, the base is a circle, right? So the area of a circle is pi r squared. So the volume of this thing would be the area of the base, pi r squared, times the height. Okay, so the trick is we need to write an expression in terms of r only. So I can't have two variables in here. Okay, I can't have the r and that h there, right? So what I'm going to do is use my answer from part A. I know that h equals 60 minus 2r. Okay, so what I'm going to do is rewrite this as pi r squared, and instead of h, I'm going to write 60 minus 2r. Okay, and that's going to be the volume. Okay, so what you guys will need to do to graph this thing, the volume will be y, and the radius will be your x value. So you're going to graph this expression. Okay, most likely use Desmos or some sort of graphing system. And in part C, they're going to have you find the radius that gives the max volume, and D, find the max volume. Okay, so I'm going to want to see a sketch of the graph, okay, just a rough sketch, and make sure we can interpret the maximum coordinates correctly. Okay, all right, so that is that. That's using properties of polynomials, some applications of it, finding minimum and maximums.